So those of you who know Marcoussis, you can imagine how it was. Yeah, he knew, but it wasn't your... So we visited Marcoussis November 11 with this kind of weather, the empty lab and everything, and still it didn't get discouraged. So I'm very glad that we are still working, we started working together. So Andrew graduated from Australian National University in '97. He did his PhD with Professor Hans Baker and David McClellan. I'm pretty sure I don't pronounce that correctly. Anyway. Then he did a postdoc in Los Alamos, New Mexico, with a group of Paul Kwiat. Yeah, I pronounced that well, right? And he is a fellow of the Optical Society of America, of the American Physical Society, and as for last year, is now a fellow of the Australian Academy of Science. Closer? Okay. If you have a look at his publication list, you will be quite impressed that he has participated in many of funding papers in quantum optics and quantum simulation, or computing, probably better. Yeah, okay. Both on the theory side and the experimental part. So I'm glad that he accepted to give a talk today and present his latest results.
Thank you very much, Pascal. It's a delight to be here. I've had fabulous time looking at all the labs, and I'm looking forward to more of it. This was the title that was just meant to get people to come, but I guess a better title would be Photonic, Quantum Simulation and Emulation, and I'll talk about what I mean by that. But it's all right. We will still annoy computer scientists. We will still intrigue chemists. That's all right, but that's the more formal title. I'm from Australia. We're very informal, so if you've got questions, please just interrupt as we go. I answer to oi, so if I'm unclear or I'm going too fast or my accent gets too strong, slow me down, please. Yeah. Slow down already, all right. Alan always wants me to speak with an American accent because he thinks that's easier. So, but I normally need to be drunk, so I wasn't game to do that today. So we'll see. This work was funded by the Australian government through Centres of Excellence, and we have two in the space of quantum. There's a Centre for Engineered Quantum Systems that's on the left, and there's a Centre for Quantum Computer and Communication Technology that's on the right. Of course, you're seeing me today, but I don't do the work in the lab. That's all done by our team of PhD students and postdocs. And it's a very friendly lab. We're from all over the world. It's mostly friendly except for World Cup time, where it gets a little tense. But we don't have enough French people. So, you know, if people want to do something about that, that would be great. Some of the work you'll see today was done in collaboration with people at Queensland, at MIT, and of course, Pascal and Olivia Gazzano here. So simulating quantum systems. There is a fantastic paper by Richard Feynman from 1982. And he was just considering the problem of why is it hard to simulate quantum systems? Atoms, molecules, little systems like that, let alone things like particle physics. And he said, we know exactly what we need to do. We need to solve Schrödinger's equation. Except the problem is the number of equations grows up exponentially with the number of particles, and very quickly you can't solve the problem you're interested in with classical computers. And if you haven't read this paper, it's very clear, it's worth reading. And in it he says, well, this is puzzling because Mother Nature herself is doing this efficiently all the time. What is she doing that we're not doing with our computers? Well, she uses quantum mechanics, so maybe we should use quantum mechanics. And it's a really beautiful paper. It's open-ended, there's not very much maths, it's speculative, and it's full of pictures of single photons and pieces of calcite, which is what we used in my lab for many years, so I'm very happy to see that. But when you read the paper, it's not clear whether he's talking about simulation or emulation. These two words in English are kind of often used interchangeably. I'm not sure of the situation in French. But here is one usage that colleagues in another field use, just so this is going to be my definition. So all Australians, of course, are obsessed by the idea of flying from Australia to anywhere in the world in 4 hours. We can't do that at the moment. It takes between 20 and 40, but 4 hours is the goal. For that, you'd need a scramjet engine. Scramjet engines are hard to understand, and there's two ways you can try and understand one. You can build an emulator, so this is a shock tunnel at the University of Queensland. It makes a physical flow of 10 kilometers per second. You need engineers to run it, and then you put physical models into the tunnel. This is a pipe, and you look at some physical measurement, and that gives you a physical quantity. So in this case, that's a holographic interferogram, and the measurements you get on the left is density, and on the right it's electron concentration. And that's one way to understand what's going on. Of course, one issue with an emulator is if you see something unexpected, perhaps the flow is coming off at an angle that you weren't expecting. Is that some effect that's going to happen out in the environment that you're concerned about, or is that maybe a boundary effect because the box was too small on the dump tank? So the other thing that you need is you need a simulator, and that's a digital model that gives you a physical quantity. And in other fields, apart from quantum mechanics, people use emulators and simulators, and they talk back and forth to one another to try and understand the problem. The advantage, well, the disadvantage, of course, of an emulator is there's no error correction. So if you see something unexpected, you don't know if that's just, that particular emulator will give you that answer. Whereas with a digital model, you have error correction. So if you pick some Hamiltonian and you calculate its properties, the answer that you get out will always be the answer for that Hamiltonian, but you've got an issue still that did you pick the right Hamiltonian? So you need to interplay back and forth between these things. It's been known for a long time that there's a quantum advantage for the digital models, that there are now ways, and I'll talk more about that. It's a bit of an open issue whether there's a quantum advantage for emulators, and people are working very hard on that. So that's the background. So what do we mean by quantum? Okay, that's a simple question, surely, but let's take an example, Zitterbewegung, which is this trembling motion of a relativistic electron. Schrödinger predicted in 1930 after reading one of Dirac's paper, which says, I think, a lot about both of them. The idea is that we've got, this is meant to be an electron going from center to right, and as it does, its wave packet trembles at 10 to the 21 hertz with a very small amplitude, 10 to the minus 12 meters. So of course, it's never been measured in practice. It's too fast and too small. But a few years ago, people realized that the Dirac equation has the same form as the non-relativistic Schrödinger equation. And we can do the non-relativistic Schrödinger equation in the lab in lots of different ways. So the first group to do an experiment on that was Rainer Blatt's group at Innsbruck. And they took, here's one of their ion traps, zooming in, that's the typical spacing of their ions. And they took a single ion. And these oscillations here, okay, I'll go back to the keyboard. These oscillations here are the oscillations that you would get from the Zitterbewegung. And you can see the match between theory and experiment is quite good. And that got published in Nature. And that's inherently a quantum system. It was a single ion. Just a little while afterwards, in the same year, Alex Zamite's group from the University of Jena did a classical simulation of relativistic Zitterbewegung using a photonic lattice. So they took a whole lot of photonic waveguides where they were modulating the refractive index, and the right is the theory, the left A is the experiment, and those dark fringes you can see as the light goes down the lattices is this trembling motion. So that would be equivalent in time slices to looking at the electron. And again, you can see the match between theory and experiments pretty good. That was a classical simulation because they used classical light. But if they'd used single photon detectors and square photon counters, then it would have been a quantum simulation. Okay? But it wouldn't have changed what they saw one bit. And then last year, there was a really nice paper in New Journal of Physics with neutral atoms where, again, they saw the same thing. So they're all looking at the same phenomena, which is this trembling motion that occurs of single quanta. But you can do it with a quantum system or you can do it with a classical system. So single quanta effects, I think, are more surprising and more publishable if they're in a quantum system that has no classical counterpart. But of course, in photonics, you have a classical counterpart, which is classical light. So the physics is the same. So the thing to ask yourself when you're investigating these things is what is of interest? Is it the phenomena? Is it the simulator that you're trying to build? Or is it a combination of both? And there's no one answer to that, but it's just something to keep in mind. This is true for single quantum phenomena. When we go to many quantum phenomena, it's no longer true. Okay, one of the things that people do to build emulators is a quantum walk. So this is the analog of random walks. They were originally known as quantum random walks in this paper by Julia Kemper back in 2003. But as Peter Knight went around telling people for many years, quantum random walks are neither quantum nor random. Okay, so they're just walks. The idea is that you have some single quantum particle, for example, a photon might come in here, and this is a series of waveguides. And so if I zoom in here, you can see that the light then just spreads out ballistically. Because at every point, the photon can choose to go left or right, and then as they come back, they interfere in the middle, and you get these interference fringes. All of this here is just a fan out to let you measure the output. Now, you can do that with classical light. It's not surprising. It's exactly what you expect. You can do it with single photons. You get this. That's not surprising. It's the same as classical light. If you do it with two photons that come in at different times, then you get a set of correlations between the outputs. That is what you would expect for classical light. But in this nice paper by Jeremy O'Brien's group, they showed that if you do it with two photons that come in at the same time, there's non-classical interference, the so-called Hongo-Mandel effect, and now you get correlations that differ to the classical light. So that's your first signature of something different to classical light, and you need multiple particles to see it. That's in one dimension. We also did a project a few years ago where we took in 6 waveguides. These were written into a block of glass by a femtosecond laser by colleagues at Macquarie University, and they wrapped into a pipe of waveguides like this. And the advantage of these is you have access to all the inputs and outputs. The inputs are here, and then you can just image that directly onto cameras or single photon counters. You can have periodic boundary conditions, so you can study things where things go around several times, and you can do next nearest neighbor coupling as well as nearest neighbor coupling as you change the ellipticity. And again, with that, we saw some difference between classical and quantum walks. Okay, so that's the technology. Is it useful for anything? And so that brings me to my first interlude in the talk. I'm going to talk about quantum biology. This has nothing to do with photonics, and I'm not an expert in it at all. If you do a search for the words quantum and biology, I think the earliest thing you find are these lectures by Schrödinger in 1943 called What is Life? And they're freely available on the web. They're well worth reading. And in it he says, yes, look, there is a quantum aspect to life. It's in chemical bonds, and that's it. He pretty much ruled out quantum mechanics as playing any role except perhaps that tunneling might enhance mutation rates. And so if you went to a physicist, most physicists, certainly when I was doing my PhD and even as recently as 10 years ago, and said the words quantum biology, you would have got, well, visually I'll show you the answer that you would have got. People were disbelieving that there was anything to understand, and that's fair enough. If you went to a biologist and you said, hey, do you think quantum mechanics plays any role in the phenomena you're seeing, the answer you most often got is maths is hard. That's not just a joke against biologists, by the way. My partner's a biologist. But it's backed up by peer review. There's this fantastic paper from PNAS 2 years ago where they looked at something like 12 years of published biology papers, and they found that for every additional equation per page in the main body of the paper, they got 28% fewer citations. So if there's any theorists in the audience, just think about that for a second, what that would do to your citation rate. But negative. So that's pretty much where quantum biology was. But it's a little bit unfair, because if you go back in the literature, in fact, as back in 1963, there was this lovely paper in Nature by, I'm going to get the pronunciation wrong, Yoshizawa and Wald, in Nature, where they said, look, there is a quantum coherent effect in vision, in everybody's vision. And the idea was the following. This is the ground state of your molecule in the eye. The visible light comes in and pumps it up to this form that's a cis form, but that's not the one that's biologically active. It goes through this avoided crossing, or conical intersection, and turns into this transform. And that transform is the one that gives you your vision. And vision is nearly, yes? Yes, that's meant to be what happens with time. Thank you for the question. Now, vision is known to be, at the single photon level, incredibly efficient, much up near 100%. If this was an incoherent process, then half the time you wouldn't get this transform, you get the cis form. but it's observed that it occurs 100% of the time. So they said, well, this must then be a coherent process, and it's happening in the warm, wet environment at the back of the eyeball. If you read the paper, the data is, by modern standards, not very impressive, but the thought behind it is, and there's a fantastic update from a few years ago on exactly the same topic. So there's one piece of evidence that biology might play a role, quantum mechanics might play a role in biology. Since then, I won't go into detail on all of them, but there's been a ton of things. The electron tunneling was thought to play a role in photosynthesis, or proposed, hydrogen tunneling in enzymes. Famously, a few years ago, starting in 2007, there was a discussion of quantum coherent effects in light harvesting molecules, so in photosynthesis. And just a little anecdote there, the gap between these experiments here had to do with how long it took to regrow some of the organisms that they were then doing the experiments on. So the actual biology takes a long time. The physics is relatively quick. And then also from 1996 onwards, quantum theorists were coming in from the outside and starting to suggest that, hey, here's some phenomena which we think we can understand better if you use quantum mechanics than your current model. Most famously was Luca Turin's work on olfaction, the sense of smell. When I went to school, I was taught that smell works by lock and key model of the molecules coming into a receptor, but that doesn't match the observed results. If you change a hydrogen to a deuterium, you hardly change the shape at all, but the smell massively changes. And Luca Turin had a theory back in '96, and he's subsequently based a very successful commercial company on this, that what you all have in your nose, what we all have in our noses, is a electron tunneling spectrometer. Cool. Don't tell the funding authorities. I should point out that that was very controversial for a long time, but that there are recent experiments suggesting that he was correct. There was also a suggestion that birds have been able to navigate by magnetic fields, but no one quite knew how that worked. So people have cut open the heads of pigeons looking for little pieces of magnet and not found any. Anything to get rid of pigeons. But there was a proposal that what's actually happening is there is a use of entangled states in the eye. And there's been theory and experiment done towards that. And it explains some of the observations about pigeons can navigate if the magnetic field is DC, but once it gets past a certain frequency, they get lost easily and so on. And then most recently, there was this article, well, most recently, it's been a few years since I did the slide, by Viserio and Plenio in New Journal of Physics, suggesting that, in fact, ion channel transport, just potassium, sodium, that well-known phenomenon, is in fact a quantum coherent phenomenon. So this is all very interesting. It's something that you can look at with a photonic quantum emulator. So let's now think about the transport problem. Say I have a chain of sites, and I have some excitation at that central site, and I ask, what happens to the excitation? Well, in the absence of loss, it just spreads out ballistically. That's that quantum walk. If I have a little bit of loss and I get it just right, I can make it look like some kind of diffusive spreading. And if I have a lot of loss in the terms of, well, noise, I keep saying loss, pardon me, a lot of noise in the terms of dephasing, I get the quantum Zeno effect, and the thing gets localized. And so a general rule of thumb is that dephasing is bad and it hinders transport and this kind of thing. There was some work by Plenio and Huelga and also by Alana Spurugutzik and colleagues where they said, well, it's not always bad. So consider the following. I'm going to have some Hamiltonian, and because I'm an experimentalist, this is how I think of the Hamiltonian. It's got some interparticle interactions. I'm going to put an excitation somewhere in that network, and I want the excitation to go to a particular site, and I'm going to call that good loss of energy. And anywhere else, I'm going to call that bad loss. I can add dephasing to that model, and I can ask what happens to the loss, the ratio of good to bad loss, which I'll call the efficiency, as I change the dephasing. And the general expectation was, well, it'll be good when I've got zero dephasing, and then as I turn up my dephasing more and more, it'll get worse. Yes, go on. So bad loss is just say the excitation starts here, goes over here, and then it gets lost to some internal degree of freedom, so it doesn't walk around the network to this point here.
Any quantity capital I here is...
Let's see. That's just some bad loss rate. Yep. So, we got other questions? Okay. So they came up with something called environment-assisted quantum transport, and the idea is the following. I'm going to have on the left a bunch of sites. Each site has loss, coupling to some other degree of freedom. And I'm going to bring in energy at this site, and I want it out there. But the site in between is detuned, so it looks like nothing is going to happen. But if I add noise now to the middle site, you can see that I come into resonance, and you can, if you believe me, you can wave your hands with this cartoon and see that the energy might move across. And that's a calculation showing that as you turn up the dephasing, the efficiency goes from under 16% to nearly 24%. So it's some kind of believable thing. So in this paper by Rabentrost and colleagues out of Harvard, they said, let's look at photosynthesis. You've got light comes into a chlorosome. It gets absorbed by an antenna. The antenna passes to a molecule called the Fenner-Matthew-Olsen complex. It bounces around the molecule, and then it goes to a reaction center where it then gets geared down and turned eventually into an electron, and this is what drives the energy for the plant. If you look at the Fenner-Matthews-Olsen complex, and it depends on which paper you read, people believe there's either 7 or more recently 8 molecules in the middle, and no one knows. There's a big argument going on. But everybody agrees that sites 1 and 6 are the ones that are attached to the antenna, and site 3 is the one attached to the reaction center. So what I have is a transport problem. I have some excitations coming in here. It's going to walk around this noisy network, and I want it to go over here. And the question becomes, what happens, what role does noise play in this? Now, figuring that out experimentally is very, very difficult to do. And you can do various theories, but it would be nice if you had a toy system to play with, and this is where the emulator comes in. So their suggestion was if you look at this, their suggestion was if you look at this blue curve here, this is the efficiency. It starts low with effectively near zero dephasing, and then there is a regime over about 2 orders of magnitude where you have near perfect efficiency of the transport. And that's actually what's observed in nature. And so this model is suggesting, well, that efficiency is due to a certain amount of dephasing. So the idea is that nature has taken advantage of dephasing, geared it up with natural selection, and this is the thing making it work. Now, to me, that looks like a fairly uncontroversial thing to say, but the model was received with skepticism, to say the least, particularly from the condensed matter community. Yes?
The unit of dephasing rate?
Let's see, inverse centimeters. I think that's 1 on as opposed to L on. No worries. So people hadn't observed this in the lab, so we thought we'd build an experiment to see if we could see it in the lab. We're a photon lab, so we'll do it with waveguides. And for that, you need 3 things. You need detuning, absorption, and noise. So to get detuning so that the sites can have different energies, you can use different refractive index waveguides, and that's straightforward to make. For absorption, that's a nice trick. You have light in some waveguide, you have it unlikely to tunnel to this waveguide, but when it does, it then runs away because there's a bunch of closely spaced waveguides, and they're within the length of the circuit, then it's unlikely to come back. And then for noise, that was a bit hard because these waveguides that we're making by having colleagues, in this case Jena, who come in with a femtosecond laser and write waveguides into glass. It's a fantastic technique because the glass becomes its own clean room. So it's much easier than needing fabrication facilities. You get good control over the properties of the waveguides, but it's impossible to introduce noise. You can't shake the waveguides. If you put a piezo on top, they all shake and just ignore you. If you put temperatures on it, they all ignore you. The common mode rejection is brilliant. So we realized that we could use decoherence, and basically a narrowband light source is going to see the right kind of couplings for the problem, but if you make the light source broader and broader, they're all seeing slightly different couplings. and so that's going to look like noise. And for that, we just did a trick where we took a down conversion source, and by changing the filter in one arm, you can get a very broad or narrow filter in the other arm. That is possibly an over-engineered way to do it, but for us that was easier than setting up a white light source. So we use the following circuit. The idea is that you'd have excitation come in at this site, you want it to go to a target site, and I'm going to put the detuning on this side. Now that looks like it shouldn't help at all, right? It's not in between. But you run the maths, and it suggests it should. If you have no noise, you should get an efficiency of 2/3, and with noise, you should get an efficiency of 80%. So, you know, a more than 10% increase we should be able to measure. These are the first results out of the lab. This is the light coming in, and this is it trapped and running away over here at the target site. And the results we're seeing, we were hoping to see 12, 13% increase. We're seeing about 8% at the moment. So we're seeing the effect. It's not as large as we're expecting, and we're not quite sure why. So this is very much a work in progress. In fact, we have a good reason. We're pretty sure the reason why is that when we made the waveguides, we didn't quite get the couplings right, but we're still proving that's the case. Okay, what else have people done with quantum walks? Remember, these are all, in some sense, classical photonics experiments. You could do this with just a laser beam. There's something called a topological phase. So these are models. You're all familiar with the idea of topology, that a ball is not equal to a coffee cup, and that you can't change one to the other. Well, it turns out if you look at the Hamiltonians in quantum mechanics, you can get properties that depend in some sense on the topology of the equation. And people had predicted that there would be these properties in some theoretical models. This top one is a model of transport and polyacetylene, also known as the Su-Schrieffer-Heeger model. And another one was from high-energy physics, a relativistic mix of fermions and bosons. But no one had ever observed these in the lab. And what you can do again with a quantum emulator is you can take a Hamiltonian and turn it into a unitary evolution, which in this case is just a quantum walk. So the idea is that the quantum walk consists of steps of you have a rotation and then a step. So the rotation is basically the coin flip. So I might have a photon come along, and depending on its polarization, if it's horizontal, I'll step left, or if it's vertical, I'll step right. And you can control a walk that way. The experiment in the lab looked like this. The translation, so we set the coin flip with a wave plate. So the light came in, say, horizontally polarized. Then we rotated it, say, to diagonal. So now I'm equally likely to go in either direction. And then depending on the wave plates here, you could change the kind of walk that you got. You could have a normal ballistic walk, or you could walk to one side or the other. And there was a prediction that what would happen, so this is the normal ballistic walk, and the two sides of the walk, the wave plates, they can have different values, but if they have the same set of topologies, so the fine details of the values don't matter, but it turns out that there is a critical value where they differ, suddenly you get very different effects. And when they're the same, the light just spreads out ballistically, which is what you expect. But when they're different, you get a bound state.
What is the difference, sir?
So the difference is, I should have got a better slide for this. The difference is the wave plate settings are putting you into a different, so if you think about what the vector describing the problem is going to do as it evolves, it can evolve with basically no phase, or it can do a full loop as it goes around. And those wave plate settings change that. I'm not doing a very good job of explaining that. The other way to think about it is if you've heard of topological insulators, this is this idea that I have in a condensed matter material, I have one topology for an insulator, and then the vacuum has a different topology. So one topology I could represent the ground state, say, by a ball, and the other one, the ground state might be a Mobius strip, or something like that. And because there's a difference in the topologies between the two insulators, you get a sheet of conduction on the surface. And this is basically the 1D version of that. And it was the first observation of bound states. We went through in great and boring detail and showed that the function was a topological function, and it didn't really matter about the exact endpoints. So that's quantum emulation. What I'd like to do now is go to simulation when you have many particles. So if we go back to Feynman, the paper came out in 1982, and if you talk to older physicists, of those who were aware of it at the time, it didn't get, I think, very much attention. Is that true, Alain? Or? Not that I'm suggesting you're an older physicist. Okay.
The picture you are shown of the calcite
Yes.
actually refers to dense inequality. Of course, it doesn't say that,
No.
but it is dense.
Yeah.
So it attracted my attention.
So it got some attention, but there wasn't a whole lot of work done. If you read the citations of the paper from 82 until 96, very little. It was a sleeper paper. But then in 96, Seth Lloyd published this fantastic paper in Science called Universal Quantum Simulators. So again, it's this idea of digital. And he said, look, you can take, the take-home message was Feynman is right. And here are the details. You can take some initial wave function, digitize it into a bunch of qubits, so two-level quantum systems, send it through some unitary evolution, so there's meant to be no loss, and at the output qubits will approximate to arbitrarily good precision the answer to the quantum problem you were trying to solve. And I did read that paper in 96, and I got very excited, and then I realized I had no idea what to do with that. I did not know how to turn it into experiment. I really did not know how to do any interesting problem. And it took nearly another decade until someone came up with an answer, which was Alana Spuru-Gutzig and Peter Love and colleagues. And they said, look, you can take Lloyd's method and use it to solve problems in chemistry. So you can turn that problem of solving these equations, the eigenvalue problem, into a phase estimation problem. And if you learn nothing else from this talk, you learn that quantum computers are really good at estimating phases. And they published a paper in Science in 2005 on computing molecular energies. And subsequently, there's been a whole bunch of work on people solving all kinds of problems in chemistry with this method theoretically. So experimentally, a few groups have done experiments. Our group at Queensland simulated molecular hydrogen, so the absolute quantum chemistry 101, take two hydrogens and put them together and look at the bonding and three anti-bonding levels. I won't go through the details, but I just want to point out two things of interest here. This is the output of the simulation. So these are experimental data points run with a 2-qubit quantum computer, but run out to, in this case, about 27 bits of accuracy. We could, in fact, run out to 40 bits of accuracy, but there's no need because when you zoom in, the agreement between the data and the theory is good to 6 parts in a million, which apparently chemists call chemical precision. We just thought of it as good enough for government work. And so that was intriguing. Philip Wolter's group at the University of Vienna then did a 4-atom molecule, a frustrated Heisenberg spin system. This is meant to be a picture of the molecule there. They did it with 4 photons. And the thing to notice when you go from 2 photons to 4 photons is you go from very good agreement, 6 parts in a million, and hundreds of data points to, let's see, 7 data points, none of which lie on the curve. Now, why is this? Is it because Philip's a bad experimentalist? No, he's a very good experimentalist. It's because of an issue to do with our photon sources, and I'm going to come back to that at the end of the talk. But this is where Pascal's work is just crucial. Basically, in photonics, we can very easily do things with 2 photons. We can kind of do things with 4 photons. And if you get to 8 or 10, forget it. And I'll say more about that later. OK, so let's just think about the quantum chemistry for a minute. The idea is this is the actual algorithm. It looks kind of strange. You take in pure qubits. So you can think of this as horizontal polarization. You make it diagonal polarization. And then you use that to control some quantum computer, which is working on a whole bunch of qubits. And you then throw them away. You don't measure them. You only measure the top thing, and you only measure 0 or 1s. And this you use to read out a phase, basically. And then you put that into some maths and turn that into an energy. So it looks like it shouldn't work. In practice, the input state here matters, and you need to prepare that with a quantum computer. So that takes a little bit more work. And this unitary gate here gets complicated for complicated problems for the following reason. If I have a 3-bot, yes?
Sorry, I don't understand what is the feedback from the microphone.
There is no feedback from the bottom part to the top part apart from the fact that they become entangled together. And that entanglement is the thing that contains powerful information. And that's a brilliant question because it looks utterly non-intuitive. It should be that if I throw away most of the information from my computer, what I have is a bad computer. Quantum computers work in this way because the information is encoded in some sense in the entanglement. This is where the power is coming from. So it's a great question. If I had, say, a three-body problem, and I had the Hamiltonian consisted of three two-body terms like that, that's very simple to write down, but what I can't do is take that Hamiltonian and turn it into a unitary that consists of some evolution between 1, 2, 2, 3, and 1, 3, because basically the maths doesn't work. So what you have to do, Lloyd introduced a solution to that, is you salami slice the problem into very small slices. And the smaller the slices, the better the approximation. And you don't have to go to infinitely good, as we've already seen with the chemistry. You only have to go up to some level of precision, which people are happy enough with. So, and if you talk to the theorists now, there are whole theorists who are writing down the quantum circuits you would need to solve problems in quantum chemistry. These are the kind of things you need to do for the different operators in quantum chemistry. And you think about what would it take to do hydrogen properly. When we did it in our experiment, we did a little bit of a cheat. If you wanted to do it properly with no prior information, it would take 6 qubits and between 200 and 1400 gates, depending on the precision. So as you get more and more gates, your precision, this is the error here. Hartrees is a unit of energy that chemists use because they must have a problem with Joule. When you get down to about this point here, which is chemical precision, you need about 600 gates. If I look at state-of-the-art that's been done around the world, controllable entangled strings of 12 to 15 ions have now been done by Rainer Blatt's group, and not yet fully entangled but nicely experimentally controlled strings of 50 ions have been done, all in the ground state. Again, the ion people can do about 100 plus gates, so my guess is a complete quantum chemistry simulation will have been done by the ion trappers within about 5 years. Okay. So does that mean photon people should give up, that we have nothing to offer? And if the answer is yes, this would be the worst talk of all time. But the answer is not yes. And so now I'm going to beg your tolerance again and go into another interlude on something I'm not an expert on, which is computational complexity. There's an algorithm called Shor's factoring algorithm, which was discovered in the mid-90s, which is a powerful way. It says if you have a quantum computer, you can solve the factoring problem easily. And we can't do that with classical computers. The factoring problem is the following. If I give you 2 prime numbers and ask you to multiply them, you can do that. If they're small prime numbers, you can do it in your head. If they're big prime numbers, you can do it on your calculator. But it's easy. But if I give you a big composite number and say, what are the prime factors, most people are bad at that. And in fact, you can show that computationally, that's a difficult problem. And with classical computers, that takes exponentially long time to solve as the problem gets bigger. So everyone can do 15. Well, some experimentalists tell me the prime factors are 2 and 7, and that's close enough to within error. But okay, everyone can do 15. If I give you 341, that's a little bit harder. If I give you 1,000,000 numbers, that's impossible. So Shor came up with his algorithm in the mid-90s and said, if you could build a quantum computer, you could run this algorithm on it, and we could read all your mail. And people got excited about that. It's redundant. It turns out the NSA is reading all our mail anyway. But Scott Aronson, in his PhD thesis in 2004, pointed out something really interesting, which I'm now calling Aronson's trilemma, which he said just the existence of Shor's factoring algorithm, not the fact that it's been built on a computer, just the fact that it exists, means one of 3 unlikely things must be true. The first one is that the extended Church-Turing thesis, which is the foundation of theoretical quantum computer science, is wrong. Now that doesn't bother me, and I'm an experimental physicist, I don't care. But it is upsetting to some people, particularly computer scientists older than me. The Church-Turing statement is this: all computational problems that are efficiently solvable by physical devices are efficiently solvable by a probabilistic Turing machine. Okay, that looks okay. I had a friend, Michael Nielsen, who helped put that into context. He wrote a nice blog post in 2004 saying, look, Church and Turing's work played the same role in computer science that Galileo and Newton's work played in physics. It put things onto a calculable basis. So some people really strongly believe that this must be true and cannot be wrong, and it has real-world implications. It could be just a philosophy debate between computer scientists and physicists, but there was in Europe about 3 years ago a fairly large advanced computation program that had as a small subset of it quantum computation. And because of that, some of the computer scientist referees killed the whole program, saying the Church-Turing thesis shows us that we don't need quantum computers. I'll scrap the lot. Maybe they're right. Maybe quantum mechanics is wrong. Okay? Maybe the problem is realistic physical devices. Now again, I don't think that's very likely, but other physicists do. Paul Davies has published a paper that says he thinks a 399-qubit quantum computer will work, but a 400-qubit quantum computer won't, because it will exceed the information capacity of a black hole or some bullshit that I don't understand. Now, as an experimentalist, I take some delight actually in the idea that if I built a 399-qubit quantum computer and it was working, and I added one more qubit and it stopped working, it was the universe's fault. That's awesome, right? And we will only find out by building it. There's no other way to answer that problem, right? So Scott Aronson in 2006, in an article in one of MIT's magazines, said it would be much more interesting than if it's possible, since it would overturn our most basic ideas about the physical world. And then he goes on to say, this is at least as important as the supersymmetry or Higgs boson. And I'm biased and I agree with him. But maybe the extended Church-Turing thesis is fine, and maybe quantum mechanics is fine. The third possibility is that a fast classical factoring algorithm exists, and that we just haven't found it yet. Lots of mathematicians have looked and think it can't be done, and lots of stuff is now based on the impossibility of doing it. Apologies for the self-quote, but it's really hard to find something interesting said by a mathematician. Actually, that's not quite true. I was talking to someone who was talking to a well-known mathematician who said he loved Shor's algorithm because it proved to him that there must be a fast classical algorithm. And I said, that's great, can I quote you on it? And he went, no. So, but all three of those seem crazy, but at least one of them must be true. And this is perfect for an experimental physicist because it doesn't matter what we do, someone's going to be badly upset, and that's a win. Okay. So the next part of the talk is how we experimentally test this trilemma with photons and with photonics. If you ask how powerful is a quantum computer and you talk to a computer scientist, they'll say, oh, a quantum computer is one that's universal for BQP problems. And if you're like me, you skipped all of your undergraduate computer science classes and you don't know what a complexity class is, and you say, okay, what's a BQP problem? And they tell you, well, it's one that a universal quantum computer can solve, and it's not very helpful. What is known to the physics community is that to have a universal quantum computer, and this has been known for more than a decade now, you need entanglement, and that entanglement must grow in a certain way with the problem size. So a small amount of entanglement isn't enough, and in fact, in more recent work a few years ago, it's been shown that too much entanglement is also harmful. So you need just the right amount of entanglement, and then you get this quantum advantage. There are no such proof for mixed state models. Or, as an experimentalist would see it, there's no such proof for the real world. Because, we've never measured a pure state. We only ever see mixed states. And that brings us to a new class of quantum computers that's been discovered in the last few years, which I'm calling here intermediate quantum computers. These are ones that are not universal in the sense that they can solve this very broad class of problems, but they can solve problems much faster, exponentially faster at least, than the best known classical approaches. And the granddaddy of them all is something called deterministic quantum computing with one pure qubit. So the idea is you go here to your local supermarket and you buy an off-the-shelf quantum computer that works with pure qubits, and you send in one pure qubit, and all the rest you send in as completely mixed qubits. So if this was light, it would be one polarized photon, and all the rest would be depolarized. And when the authors first presented this, Manny Kinil and Ray LaFlamme, in the late 90s, they presented it at a meeting at Los Alamos. I said, well, that will be useless because the output state is arbitrarily close to completely mixed. There's no information. And I was massively wrong. There's a whole bunch of problems that people have now found that this solves more efficiently than any known classical algorithm. The most unlikely one, in my opinion, being the Jones polynomial and knot theory. It's just such a strange thing. And how the computer works is it should look a little bit familiar if you remember the quantum chemistry circuit. There's one pure qubit controlling a unitary, and I'm only measuring the output. I'm throwing everything away, except this time now the input is not specially prepared by another quantum computer. It's perfect noise. And this is powerful. We had trouble believing that, so we did a little test experiment with 2 photons more than 5 years ago. Alpha here, if it was 1, it would be a pure state. We were close to pure in the lab. And basically, if you can see fringes, then you're seeing a quantum advantage. And as we turned alpha down, you can still see fringes. And in fact, the theory shows that as alpha goes arbitrarily close to 0, but doesn't become 0, you still retain a quantum advantage over the best known classical approach. It's still exponentially faster. But hang on, I said before, in answer to your question, the advantage was coming from the fact that I'm entangled. Now if I'm sending in noise, there's no entanglement. So where's the quantum advantage going on? And there was a great deal of discussion about that for a few years. And there's a nice review article about that in Nature. It turns out that for mixed states, there's a new kind of quantum entanglement, a new kind of quantum correlation that lies beyond entanglement called discord. And in all of these problems now, the discord has found to be strongly correlated with quantum advantage. But as far as I know, no one has proved that it's the thing that's enabling it. So that's still an active area. But this is interesting for an experimentalist because now there's a much broader class of problems. Other intermediate quantum computers include something called a temporally unstructured quantum computer, a permutational quantum computer, and boson sampling. And these are all in utterly different physical systems. The boson sampling, you'll hear a lot more about. It's photons in a network. The others are spins interacting. But if you talk to a complexity theorist, they say, look, we've got a well-founded suspicion that all of these things are interrelated at some fundamental level. And so with that in mind, and given that we'd already explored DQC1, we started playing with boson sampling to see what we could learn. So here's boson sampling in principle. It's really easy. I'm going to take m quanta in some distribution of modes. Think of these as photons, if you like. Send them through some unitary network. That can be just a bunch of beam splitters. And I'm going to ask what happens at the output. Do I get 5 in one mode, or are they equally spread across all the modes, or is there some bunching, or whatever? Let's just think about this, by the way. If I had a working quantum computer, could I model this with a quantum computer? And the answer is yes. Each of those quanta into n modes, so if I say I had 3 quanta into 6 modes, the fact that I've got 3 quanta means that I no longer have q bits, but I've got q trits. So to model a q trit, I need a network of q bits. And the maths is that's the number of q bits I need. And then if I have an arbitrary unitary, which this can be, on some network of qubits, I go to Nielsen and Chuang, which is the textbook in quantum information, and I look up the order of the number of gates I need, and I need that many. So let's put some numbers on this, because I always get lost at equations. So if I had 3 photons going into 6 modes, and I wanted to model that with a perfect quantum computer, I'd need 12 qubits and 1 billion gates. That's a lot. If I had 10 photons going into 100 modes, and this answers Pascal's question on why I keep obsessing on 10 photons, then I would need 400 qubits on 10 to the 246 gates. Okay, now this is a straw man, because no one's suggesting that you would actually solve this problem with a quantum computer this way. But it makes the point that people often don't appreciate, that quantum computers are only useful when you have some deep structure or symmetry in the problem you can exploit. This is what you need if you're going to do an arbitrary unitary about which you know nothing. And this is why Shor's algorithm was so revolutionary. It got these numbers way down. Okay? But I guess the take-home message here is photons are not qubits, and that's a good thing. Okay? They're real quanta. So no, we wouldn't model this with a quantum computer. What about classically? So classically, we know how to solve it with a classical computer. We write down the unitary, and then we say, look, I only need to worry about the rows where I'm sending in a photon. So if I'm not sending in a photon in mode 3, it's not going to be involved in the problem, so I can just take it out. And I only need to take the columns where I'm going to measure a photon. If I'm only measuring at the first 3 outputs, that's all I care about. And I look at that submatrix, and that submatrix has all the information about the problem. It's got the probability amplitudes. That's it, I'm done. So all I need to do is, for fermions, that's really straightforward. If I have some non-interacting fermions, so not electric charges, but some mythical thing, and I send them through this network, all I need to do is calculate the determinant of that submatrix. And that's really efficient and easy to do. It scales as n cubed, so that problem is in complexity class P. And you can do that quickly on your laptop. And this was first pointed out by Barbara Terhal and David DiVincenzo back in 2002. What about bosons? So look, when I went through undergraduate, I came away with a very firm opinion that bosons were way simpler than fermions. Okay? It just, everything kind of indicated that. For my curiosity, hands up if you think that's true also. Okay, all right. Who's listening? Hands up. Okay, all right. Sorry, I've been teaching too long. All right. And so I was shocked when it turns out for this problem, you need to calculate something called the permanent. I'd never heard of that. But basically, it's just the determinant where the minuses are changed to pluses, so that doesn't look like a big change. But when you try and calculate the permanent, it grows as n factorial. So for large n, that means it's growing faster than exponentially. It's growing as n to the n. And that problem is in a complexity class called sharp P. And if you talk to computer scientists, they're very hard to pin down, but they strongly believe that to be classically intractable. Certainly no one's got any clue how you would solve that efficiently. So in this case, this very simple problem, bosons are far more complicated than fermions. What do I mean by NP versus P? An NP problem is one like the travelling salesman problem. So I ask, is there are there any graphs which cost less than some resource X? Is there some way of getting across the bridges which would take less than some time? A sharp P problem is asking how many graphs are there where that's true. So the first one's a decision problem. Yes, no, is there an answer? The second one's a counting problem. And counting problems are harder than decision problems. So this boson sampling problem is much harder than an NP problem. So that got people very excited for a little while because you would think, well, hang on, this linear optical network is outputting the permanent. You know? Can that let us solve NP or sharp P problems? And you could make a lot of money very quickly if you could do that. The problem is the device outputs the probability amplitude, that's true, but what you can measure is the probability. And this is a really interesting observation for me. You lose just enough information there, it's kind of a censorship principle, that you don't win. Because you measure probability, that extra information in the phases that you lose is the information you'd need to calculate the permanent. And so you lose. So is it interesting? So no, we can't become rich overnight. It turns out even asking the simpler question of how often do I see a particular output, so that's the sampling idea, how often do I see one photon at every output, is also a hard problem on a classical computer. So Scott Aronson and Alex Arkhipov, their main result, which is in this 90-page paper, is if a classical computer can do the same thing in polynomial time as that quantum circuit, then something called the polynomial hierarchy collapses. And my mental image of that is this, which means I have no idea really what it means that the polynomial hierarchy collapses. I had more of an idea after I talked to Scott, and then he's got a nice book on quantum computing since Democritus. And he does go through and explain there. But needless to say, computer scientists think it's really unlikely. So where does experiment come in? So building a large-scale boson sampling experiment would be the strongest evidence that the extended Church Turing thesis is not the way to go. Okay, you can't disprove it because it's a statement in the asymptotic limit, but you can make it seem very unlikely that there's something correct about it. What do we mean by large scales? Well, the calculations that Scott did suggested on the order of 20 to 30 photons into 400 to 900 modes would exceed the calculational capability of the entire planet. And so within a smaller problem, like 10 photons into 100 modes, it's very believable that doing that experiment would be far, far quicker than calculating the answer So let's look at what I mean by that. Let's look at practice. So here's the challenge. I'm going to hand you a black box unitary. It's an optical circuit. And I'm going to hand it to a classical computer scientist and a quantum computer scientist. And I'm going to tell them which inputs we're going to send into the circuit. Say 2 photons into the first mode, 1 into the second, none into the third, blah, 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 blah. And I'm going to say, how often do you see 1 photon at each output, right? This is not a terrible, devilish problem at all. It seems a fairly fair thing to ask. The classical computer scientist says, no worries. I will measure the unitary because, I've just been handed it by an experimentalist. I don't know what it is. But then once I know what it is, I take the submatrix and I calculate the permanent, and I'm done. That gives me the output amplitude. From that, I can get the probability. The quantum computer scientist says, thank you for your unitary. I'm going to stick my bosons in, and I'm going to measure how often I see 111 come out. And I do that enough times that I can build up a probability from the frequency. Who wins as things get large? Well, in a perfect world, the quantum computer scientist wins. And we've seen that already. This problem gets very hard computationally. But what we don't know in reality is what are the effects of mode mismatch, photon loss, detectors not being quite what they should be, all the things that you know better than me really happen in the lab. So the only way to find out is let's go. Which bosons could you use? Any boson. It could be neutral atoms, it could be phonons and ion traps, it could be bosonized fermions, so superconducting Cooper pairs. Having looked at labs yesterday, I'm now thinking very hard about polaritons and plasmons. We used photons in linear networks because they've got the best coherences of any boson, and we're a photon lab. So this is some optics. So it's an optics audience, so this is good. You can take any optical network and split it into a network of beam splitters and phase shifters. This is an old result by Rechen, Zeilinger and colleagues from '94. How do you measure what that network is efficiently? Well, one way that people have suggested is that you send in multi-photon states and then you measure what comes out in terms of photon counting. And that kind of works, but in practice it's very noisy, so you might get out from that maybe 40 different unitaries and you have to pick the one you like best. So I don't like that so much. And also it's the same thing that you're trying to do with the boson sampling experiment. So I'd like an independent classical measure, not a quantum measure. Well, the other way to do that is you could just put it in a whole bunch of nested interferometers and carefully lock them all up and then change all the phases, but that's too much work, so no one does that. The third way is it turns out you can use just pairs of classical laser beams. Let me go into detail here. So here's the unitary I want to measure. First I send in a laser into mode 1 and I measure what are the intensities on the outputs, 1, 2, 3 to 6. And that gives me the real parts of the first row of the unitary. Then I send it into mode 2 and I send it into mode n all the way down, in this example to 6. That gives me the real parts, that's the easy part. Saleh Rahimi Kashari, a PhD student of Tim Ralph's, we were being grumpy about how hard this problem was, and he said it's really easy. All you need to do is the following. You take your coherent state and you split it into a pair of beams, and then you wiggle one of the beams with respect to the other. And now at the output you see fringes. And now what you do is with respect to this fringe here, you measure what is that distance in phase to the next peak there, the next peak there, the next peak there, the next peak there, and that is the phases of the matrix. And so you do that for mode 1 and 2, mode 1 and 3, all the way through to mode 1 and n, in this case 1 and 6, and that gives you the unitary. And that's efficient, classically efficient. So you can measure the unitary efficiently. This is for our experiment. You get moduli and phases that look like this. This is what we did in our lab. In the same way that when you do state tomography or quantum state tomography, the thing you get isn't quite physical. This thing isn't quite unitary. You have to do a little bit of manipulation to get it into the unitary state, and that's all described in the paper. And then you can use it to predict probabilities. But the problem with that is in the lab we have detectors, and each detector has a slightly different efficiency. And knowing that to 1 part in 1,000 or 1 part in 100 precision is a pain. And it also depends effectively on the losses in each path. And so we don't really want to do that. So instead what we do is we look at something called the Hongo-Mandel visibilities. And this is the idea that if I have 2 photons coming into a beam splitter and I have them come in at different times, that's going to occur with some probability. Because they're different times, they're distinguishable, PD. Or if they come in at the same time and they're identical photons, then that happens with a different probability, which I call indistinguishable, PI. And by taking the ratio of those two things, I can calculate a visibility. And that visibility, because I'm measuring that with the same detectors, is insensitive to differences in detectors. So I can measure that very easily in the lab and compare it very well with my prediction. That's the kind of thing that we measured in our experiment. So how do you make a unitary? There's lots of nice ways to do it with surface waveguides or integrated waveguides, lots of really quite clever things. We did something very simple. So we published our result in Science last year, and then there were 3 papers shortly afterwards, all with different ways of doing the unitaries. Ian Walmsley's group also in Science, Philip Volta and Fabio Schierano's groups in Nature Photonics. The way we did it was we took the unitary and we said, look, we want to get 6 modes. How can we do that in an equivalent circuit diagram? And it turns out the easiest way was we took a non-polarizing fiber beam splitter. No, that's just not going to work. Okay, a non-polarizing fiber beam splitter seen there in yellow. Except, of course, the manufacturer says it's non-polarizing, but in reality it's polarizing. And we said that's not a bug, that's a feature. So what we'll do is we'll change the polarizations going into that, we'll change the coupling coming out of that, of single photons, and so that gives us, in fact, 6 modes out of a 3 spatial mode device, but putting polarization analyzers at the end of it, and that lets you program up, by changing those polarizations, a very large 6x6 unitary. It's not an arbitrary 6x6 unitary. You can't get to every point in the parameter space, but you can get to a lot of them. So we did that. We had photons, and I'll talk more about the source in a minute, from down conversion. And there's 6 choose 2 ways of doing that, so you get 15 visibilities. And there they are. That were the ones measured by a quantum computer scientist. The orange bar is the value. The little, oh, it's not orange, okay, it's grey. The grey bar is the value, and the little darker bar at the top is the uncertainty. Okay? The classical computer scientist, here's the envelope of what they measure. The darker bars there are their uncertainty. Remember, they had to measure a unitary and then do their calculation. And how well do they overlap? Well, it's pretty good. You run all the various combinations, and it looks okay. They don't quite match everywhere. You can send in 3 photons. There's 20 ways of doing that. You'll notice the gaps are getting bigger. Okay, let me zoom to that because that's annoying. So you can see there, zooming in, that the quantum computer and classical computer scientists don't agree to within error. And that's horrible for an experimentalist. And it gets worse with 3 photons. It's really annoying. What's going on? And what's going on is the down conversion source is the problem. So a down conversion source works by I have a nonlinear crystal, a high energy, coherent classical laser beam comes through, and one of the photons in the beam every now and then splits into a pair of lower energy photons, conserving energy and momentum if you count the crystal. The problem is, some of the time, with some efficiency, that happens at eta, but some of the times, instead of getting a pair of photons, I can get 2 pair of photons. And sometimes, eta cubed, 3 pair of photons. And that's a problem. Those higher orders of photons, as I make my efficiency better and better by turning the pump light up further and further, they come up faster. You can see they come up quadratically and better. And so now I no longer have single photons coming in, I have multiple photons coming in. And so what I'm doing with the quantum computer scientist is further from the ideal experiment. So this orange curve here is showing that as I turn up the pump power, the L1 norm is just the distance between the classical and quantum computer scientist predictions, it gets worse and worse and worse. And this black curve is showing that the distance between what the quantum computer scientist measures with their single photon states and what they'd measure if they used a classical laser beam, it gets less and less. So it's telling us something we already know, which is in down conversion, the brighter you get, the more classical it gets. And so you have to run at low power. And this now brings me to the challenges for photonic simulation, which is if I want to do a large-scale simulation, I need 3 things. I need a source of many true single photons. I need good detectors, and I need good networks. Okay, detectors, I'm happy to say, is a rapidly becoming solved problem. Not commercially solved, but solved. So there are now available 2 labs around the world, photon number resolving detectors that are efficient, that are fast, that are quiet, and that are extraordinarily broadband. There's no one detector that has all of these things, but it's getting close. There are now fast detectors that have only 95% efficiency, but still, 95 is okay. The dark noise at 800 nanometers, you can get less than 1 dark count a day kind of thing, so it's effectively 0. So in our lab, we were trying to make a very efficient source to detector setup with an entangled source. We had an efficiency of 63%, and we used that for something called quantum steering. We'd got it up to 74%, which had us very excited because we thought we might be able to shut the detection loophole in Bell's inequality. And then Anton Zeilinger's group beat us last year, as did Paul Kwiat's group. So now we're going to pretend we never wanted to do it anyway. No, there's still other uses for an efficient source and detector. It's okay. So detectors, I'm hoping to convince you, it's okay. We're okay. What about networks? Many of the people in the room know far better than I that there is a lot happening in networks. One of the things we've been doing, because it's cheap and relatively easy for a university without access to very expensive fabrication facilities, are these integrated waveguides, where you come in with a high power laser beam and you write into a glass block. And you can do 3D structures. So this one here, this network here, is something that my PhD student Devin Biggerstaff has been working on. It's meant to be the same arrangement of things that you see in photosynthesis, and we're looking at quantum walks around that. Martin Ringbauer is working on a entangling gate in these things. So they're quite good. You can put heaters on them and make them reconfigurable, which is not fast, but it means you can tune your unitary, so it's something that's hard to sample. If your unitary is identity, that's very easy. Your computer will always beat your experiment. The loss is not all that we'd like it to be. Single photon people are very, very difficult to work for. You come along and you go, I've got the loss down to 0.1 dB, and we go, really? We were really hoping for 0.0001 dB. And then we get slapped. So, but things are on the way. Down conversion is terrible. So we know pretty much everything about down conversion. We know the spatiotemporal modes, we know how they change as a function of angle, we know the frequency spectra, we know the polarization properties, we know the temporal properties, but it's terrible. It's the gold standard for single photons, but it's terrible because of the following properties. The first thing is it doesn't happen very often. Right? So I can get millions of 2-photon events a second. I can get tens to hundreds of thousands of 4-photon events a second. 8-photon events, I can get 8, 10 of those a day. 10-photon events, I can get once a year. Okay? It does not scale well. And of course, the other problem is this higher order photon terms, which I've already showed you cause problems. So we need much better sources, and that's where I'm delighted to say Pascal's 2010 paper in Nature came along. I'm sure you're all familiar with it. In that, she and her team showed that you had high efficiency photon sources, 40% compared to 10 to the minus 4% for down conversion. They could make separable or entangled pairs of photons using this double pillar structure. They came out on higher order spatial modes, but that's not necessarily a killer. If you knock off one of the pillars, you get a single photon source that comes out in 0,0 spatial mode. In work she did with Olivia Gazzano and my postdoc Marcelo Almeida, they showed you could get this very efficient 79%, very close to being a true single photon source, and in particular the work that Marcelo and Olivia did, they then used that to build a linear entangling C0 gate. So this is an incredibly promising source, and the current project we're working on is we'd like to take these single photon sources in a pillar, pump it with n pulses in a row. N can be 4 for public purposes and 10 in your head, and then turn it into n output spatial modes. And then we want to do boson sampling with it. And now I hope I've convinced you that's an interesting thing to do. That if we are able to do that for maybe 6 or 7 or 8 photons, as we add one more photon each time, the computation time is going to blow up factorially, but the experimental time is only going to change by 0.8. So that will be, I think, really, really interesting. That's what we'd like to do. One of the things we'd like to do. The other challenge, of course, is you want to do, we need theorists to look at these intermediate quantum computers, and all these simulations are done, if they're not a full digital quantum computer simulation, they're done in the absence of errors. handling errors, and that may kill you. So it might be the fact that, yes, the theory all works if you've got 100% indistinguishability of the photons. What happens if you've only got 99%? The early theory suggests that's going to be okay. Fine. What happens if you've only got 80%? No one knows. When you get 0%, it's not going to work. So there must be some phase transition in complexity in between, and no one knows what's going on, but there's a lot of people looking at that. Let's see. Of course, the other thing we'd really like to have is nonlinear operations at the single photon level. So some of the work we've been doing, this is just to touch on, and then I think I'm pretty close to done, is you can take rubidium-85, have meter and signal fields at 780 and 776, and you confine your rubidium in a hollow core optical fiber. This is a Kagome lattice, and the core is about 30 microns across. And we have a colleague at the University of Adelaide, Andre Luton, who is very good at filling those things with rubidium. It takes him 3 months, 6 months. They make these pipes, put them in, pump on one end, put in rubidium. But at the end of that, they've got 15 centimeters of rubidium with a great optical confinement and an obscenely good optical depth. So the first thing we did was with coherent pulses, is we got, at very low powers, 0.7 microradians per photon phase shift on average. Except the absorption was quite high, and you don't want that. So with 0.5% absorption, you detune a little bit. You don't lose very much. You go from 0.7 to 0.13 microradians per photon. Okay, we published that in PRA. What we'd like to do next with that is put in true single photons. So we have a team building a very narrow band single photon source. It's not state of the art. State of the art is Alexander Gaeta's group on the east coast of the US. Last year, Nature Photonics, with a much smaller hole, instead of 30 microns, 6 microns, they're getting 3 orders of magnitude better phase shift per photon. But the problem is the duty cycle of that experiment is about 23 hours. So it works for an hour, and then the rubidium plates up the inside core. Then they have to come out with a high power laser and pump on it for 23 hours to try and blow it out. So that's not a scalable technology, but it's, you know, these are baby steps, but we're getting there. I'm trying to convince you that at least now we're seeing mechanisms where we could get strong nonlinearities per single photon. And looking at the labs I've already seen here, I think we've got some real prospects for getting those numbers up a long way. All right. Okay, I'm going to skip this, I think. How am I going for time? Negative. Oh, yeah, no wonder everyone's falling asleep. Let me go right to the end. We can slip all the closed time-like curves. Just go straight to the end. Here we go. So what are the take-home messages from the talk? There's a technical message, which is we've experimentally verified that M-photon scattering processes can be done in an interesting way in the lab. There's take a step back message, which is photonic quantum simulators are capable of hard computational problems without building a full universal quantum computer. And that really was not known to be true 2 years ago. So that's interesting. And an advertising one, quantum photonics is back in the game. So thank you very much for your attention. And if you've got any further questions, please ask. Thank you. Oh yeah, that's typical working conditions in our lab.
Okay, so thank you, Andrew, for this talk. Are there any questions? Who wants to start? Aha. Yes.
About this boson sampling thing, there are only photonics ways, or are there other atoms or whatever?
So the question from Philip was about these boson sampling things. Is the only way to do it with photons, or have people explored other ways? So Daniel James had a theory paper 2 years ago in PRA, or PRL, I think, suggesting ways you could do it with phonons in an ion trap, where you would then use the ions as the beam splitters and interact them that way. So that's, and there was a recent paper, I think 2 weeks ago, by another group of theorists suggesting a similar thing in ion traps. I haven't seen any detailed theoretical things, but looking at some of the other boson systems around, I think you could do some interesting stuff, perhaps with the polaritons. In fact, that's very intriguing to me. And the neutral atom people, of course, have been looking very hard at this because they are beautiful controller bosons. If they get into a mod insulator where they can have one atom per site, and then they can control the circuit in real time, they should be able to get to, I think, interesting things very quickly. Having said that, I'm not a neutral atom person, so it's probably much harder than I just said. I mean, you know, for photons, you've just got to put some photons in, right? How hard is it? But, so.
Yes, another question. Yeah, you did not, well, you sort of told it, but the ultimate criterion for quantum simulator is to be able to simulate some things that you cannot really, there is absolutely no way to compute classically. So your boson sampling or permanent calculation is an example. So you think it's the best example of?
Oh, no, it's not the best example, but it's one that, and I mean, it's not really interesting in terms of what you really want to do with a quantum simulator is find new physics, right? As physicists, I'd like to be able to explore phase transitions of hard problems and things like that. And this won't do that. This is a simulation of itself in some sense, right? It's not interesting from that point of view.
It's a computer science problem.
Yeah, it is a computer science problem. That's really why I tried to set it up that way. The only reason I think this is interesting to us is because it solves a bit of a debate that is that interface of information science and physics. And I think that's really interesting. The reason it's able to do that with such a small number is most of the problems that people are looking at blow up exponentially with the problem size. This one blows up factorially, which is why suddenly it is interesting to be able to do it with a handful of particles or a few handfuls of particles, as opposed to, you know, Shor's algorithm. If you wanted to do that without error correction, you'd need, if you're using, John Preskill had a paper a few years ago that said you'd need on the order of 4,000 qubits and a subsequent number of gates. That's without error correction. Then with error correction, it's bigger. So, you know, that's a hard problem, right? If you look at Rainer Blatt's technology where the gates, they're using a common mode, they can get down doing, you know, factoring 15 from 4,000 to a few hundred gates. But it's still, that's a lot, you know. And so if we can do a really hard problem, you know, I don't think it will lead anywhere. Other people are actually looking to ask, will this lead to interesting abilities? I don't know. I don't know enough.
Well, if due to this, yes, n power n blow up, it may still, according to what you say, be the real example where you can just blow up any kind of classical
Yep. So this would definitely be an example of something that you can just do much, much faster than any known classical computer.
Better than D-wave.
Better than, yes, we should, if we do it with photons, we should call it C-wave. Yeah, no. Far better than D-wave.
Okay, thanks.
Hard to be worse.
Are there other questions?
I come to your interlude about quantum physics and biology.
Yes.
I've certainly not looked in a comprehensive way in all these papers, but each time I saw a paper where they claim entanglement, actually it was just coherence and not entanglement. Do you agree, or do you have examples where
so
it is
nearly all of
real entanglement?
Nearly all of the papers I showed, I think they were claiming coherence, coherent effects, which
Some of them claim entanglement.
the only one that I'm aware of that is really strongly claiming entanglement is the suggestion that the bird navigation is the difference between a triplet and a singlet. And it's only entanglement in the sense that, well, a triplet and a singlet are entangled states. But they're not claiming any kind of, you know, computational advantage due to the entanglement or anything like that. But even if it's just coherence, the fact that you can have quantum coherent behavior in warm-wet systems was pretty surprising to people. Yes, but that's right. But the scaling.
When do you think it becomes interesting?
Now that's okay. So the question is, when does it become interesting? At which scale? And Luca Turin's work on olfaction, that's much bigger scale than just, you know, immediate bonds. And there he's proposing inelastic electron tunneling, which you're going to call a quantum coherent effect, I guess. That's getting quite large. I don't know the answer, in fact. The question of has nature used noise to get, and the interplay between noise and coherence to get better efficiency in photosynthesis, I think that's going to be answered in the next few years. And that's, you know, what scale is that? That's mesoscopic. These are very large complexes of molecules, but it's certainly not microscopic. You know,
and of course, there is another way of thinking. When you have a behavior of a classical light, okay,
I completely agree. In fact, I added this slide because I don't know if you recall, but you nailed me at a meeting a couple of years ago on this question. So this is particularly why this slide was here. And really the question is, are you interested in the physics of the phenomena, in which case you can do with a quantum system or a classical system if it's a single particle phenomenon, it doesn't matter. Or are you interested in the simulator, or are you interested between the interplay of those two? So one of the nice things about all the tools that we're going to use for these photonic emulators is we then hope to use those to do simulators of harder problems in condensed matter where you need multiple particles, for example. But it's baby steps in terms of the technology. But I agree, look, all of Alex Zamite's work, it's beautiful work. He takes these lattices, he can do Kagome lattices, graphene lattices, he sends in classical light, and he's doing simulation of, tachyons versus tardons. He's doing simulations of Dirac cones and graphene, but it's all classical. He's simulating quantum things, but he's doing it with a classical system, because in the end, he's using a wave equation simulator. Yeah.
We have to stop, but just as an example of this kind of problem that you very correctly raised, you were not born. When I was a student, okay, it was all about optical way of calculating Fourier transform.
Oh no, I remember that.
And that it was in the 60s.
Yeah.
And of course, the computer were very slow. They are not yet invented the fast Fourier transform algorithm. And obviously, doing it with an hologram and something like that was fantastic. Okay, so it was a kind of simulation.
Yeah.
And if you want to call it a quantum simulation, why not? But then, at least optical simulation. And then what happened? Two things. First, computers, we know, are faster and faster. But second, a big mathematical progress, invention of the fast Fourier transform algorithm.
Yeah.
And it totally changed the scope. But at that time, it was clear that the simulation with light was much more efficient than anything known at that time.
That's right.
Except that there was noise. It was awful.
Yes, but those photos of the moon, for example, they used the Fourier transform methods to take out the grid maps. They're beautiful, right? They still work today. And you're right? It might be possible that people will find a whole new class of algorithms to do these problems, and there may be no quantum advantage over the classical world. The quantum computer scientists of Scott's generation now think that's very unlikely for reasons that I can't explain because I don't really understand them. But this is what we're going to find out in the next few years. So it might be just a repeat of last time, but it may not. We may find new science by doing this. So. Oh, no, it's fine. But no, I agree. I mean, Alex constantly gets in his papers referees saying, well, you're claiming you're simulating the Dirac equation, but it's just you're doing classical optics. And he says, yes, I'm simulating the Dirac equation with classical optics. That's all I'm claiming. The quantum advantage, for that you need multiple quanta. I'm quite sure of that. Yes?
You explained that the parametric downconversion sources are not efficient, not bright, but they have very high indistinguishabilities.
Yes,
with solid-state sources, okay, it's going to be really bright, but less visible. How bad is that?
So the question is, how bad is it the fact that the solid-state sources are very bright, but they're not quite as indistinguishable as the downconversion sources? And the answer is, in some sense, we don't know. So for example, for the boson sampling, we know that if it's got perfect indistinguishability, it's much harder. We know that if it's got 99%, it's still much harder. We know that if it's got 0%, it's easy. But what we don't know at the moment is at what point in between does it become an easy problem? And how does that scale with the instance of the problem size? So surely as you go to thousands of photons, they must be up near the 99%. But maybe for 10 photons, maybe 80% is enough. Oh, and that brings me to, in fact, let me just skip to one slide here. When I introduce the determinant and the permanent, it turns out they're special cases of something called the immanent. I'd never heard of the immanent either. The immanent is the same terms, but now with arbitrary phases between them. Mathematicians have known about this for a long time, and it turns out in the lab, when you don't have a perfect indistinguishability, you're no longer operating on the permanent, you're operating on the immanent. And so we're actually doing some theory work with Barry Sanders, and he's also working with Philip Walter's group to kind of explore that space and find out where does that cliff come. So it might be that 80% is enough. Obviously, it's your job to get that up to 99.9, but you know, it might be that 80% is enough to do something interesting that we can't do with classical computers, which is, you know, one of the goals. The other longer term goal for the field, of course, is we want to get to new physics that we can't do. And for photonics to play its role in that, it's going to need, I think, not all of my colleagues agree with me, it's going to need nonlinear elements. And so that's another really important part. The ion trappers are eating everybody's lunch at the moment. There have been some nice neutral atom simulations of interesting effects, and they're scaling pretty well. But in terms of digital quantum simulators, the ion trappers have big numbers of qubits, they can control them, they can do hundreds of gates, and they've got a real clear path to scale that up to bigger numbers. So given that that's the challenge, you know, will photonics play a role in this? The other question in quantum information is people keep saying things like, if you want to do quantum communication, you need photons. Maybe. But when they were making Lord of the Rings in New Zealand, they were generating a terabyte of data a day, back when that was a lot of data. And they were doing all the digital post-processing of it in Los Angeles. Now, there's plenty of dark, unlit, available fibre between New Zealand and LA. They could have easily sent it there. But the cost, they couldn't get Telecom New Zealand and the US telecoms to agree on a reasonable cost. So what they did for every day of filming of Lord of the Rings was they took the day's filming, put it onto 2 hard drives, gave them to an intern, sat them in first class, flew them to LA, handed over those drives, picked up yesterday's drives, flew straight back to Auckland, handed them to the director, Peter Jackson. And it might be with quantum information, that might be the better way. If we get long-lived quantum memories, we might be better off just generating a whole bunch of spins, putting it into a quantum hard drive. You know, 300 spins, 300 qubits in a quantum hard drive contain more information than the number of atoms in the universe. So maybe that would be cheaper. It's only 20 hours to Australia from here. If I'm trying to send a lot of photons, single photons to a fibre, down a fibre to Australia from here, without amplification, forget it. I'm going to need a quantum repeater. And maybe it would be cheaper just to send a hard drive. So I don't think photon people should get very arrogant about, oh, we'll always have a place in quantum information. Maybe we will, maybe we won't. But we just don't know.
But you mentioned that the ion people are eating everything on digital quantum.
On digital.
But remember that the final paper was not about digital quantum computing. It was about quantum simulation.
That's true. The Feynman paper was about quantum simulation, and there I think the neutral atom people have a beautiful testbed system. And I think they're going to start doing interesting things, in particular in terms of phase transitions. And one of the things I'd like to talk to some of them about is at the moment they've been doing all highly ordered systems, and that's kind of boring. It turns out if you add noise to the system, you can see phase transitions of behavior that you can't predict from the entanglement, but you can predict from the discord. And so there's a real beautiful play space there that is just really hard for theorists to do, and it's much easier for experimentalists. I mean, noise in experiments? Come on, it's what we do.
Okay, I think we will probably stop the session now, and thank Andrew again for this
Thank
very
you.
interesting talk.